And first up is Alex. Alex Newman keeps calling himself a data janitor. I don't know. But anyway, Alex is from Planet Labs, and he's been doing some really interesting stuff with, well, a bunch of software that we talked about. So there you go.
Just so everyone knows, GitHub is back up. So if you need to actually check stuff out, that's not the way it works. Let's see how the demo guns actually work here. Okay. So this is especially cool because I got to work with Arvin in open source and the previous companies, and it's especially nice to share the stage with them. So cool. Planet Labs. So I want most of this talk to be a pretty open format for you guys to ask me questions, but since we're not kind of the traditional Silicon Valley company, I thought I'd spend a little bit of time trying to tell you what we do and give you some motivation for our existence. So the title of my talk is Imaging the Whole Earth Every Day. We will be able to take a picture of everywhere there are humans on the Earth every day in a couple months. This probably changes your relationship that you have with your planet. And we take this responsibility very seriously, but it's also kind of a cool, positive thing so that all of you will have access to a time machine where you can look at the changing status of your whole world. So I'm going to get into my little bit of this, but for now I'm going to talk a little bit about what that really means and who our partners are. So most of what people use Planet Labs for now fits into one of these little boxes. We do scientific imaging where we'll collect near IR data from across the world so that we can remotely sense chlorophyll levels in plants to help people more effectively deploy fertilizer. We do a lot of emergency response. We provided free data to the Nepal disaster. We provided free data for the Indonesia disaster. We get some support from NGOs, but I always like to bring this up as something that we do because I think it's core to the culture of Planet Labs that we are here to try to help the Earth, trying to help everyone here on planet Earth. I don't know if you guys remember that famous photo when people first saw the Earth and realized we were kind of all in this together. I think that when you're in the space industry, that becomes very, very prominent in your thinking. So to image the entire world, we do need to launch hundreds of satellites. So the individual satellite itself may not be as high resolution data as you're used to. I kind of look at this as a good thing. I'm not necessarily sure I like the idea of people reading my newspaper over my shoulder. But it's important to us that we have resolution sufficient for our humanitarian and agricultural and construction goals. I don't know how much you guys know about this stuff, and these are the immediate revisiting rates that we're expecting this year. Although I think we should get to daily by Q4, or somewhere between Q4 and Q3. But yeah, we actually manufacture the satellites in San Francisco. We don't build the solar panels, but we do assemble the satellites and do a lot of the pick and place and construction in San Francisco. It's probably not the type of satellites you're used to. So our satellites are actually off-the-shelf parts. So we run Linux, we have Python in space. Soon we'll have Rust in space. We've crashed more satellites than anyone else has ever launched. So this is what it takes to image the whole world every day. I think that satellite number is a little low. But we keep our altitudes at sun synchronous, so 475 kilometers is not very high up. I guess it's like LA to San Francisco, smaller. But they are traveling at 30,000 miles an hour. So most of the hard part about rocketing them up is not getting them up, but actually getting them going sideways enough so they don't come down. And we keep them at 475 kilometers, so that way an individual satellite will pass over the same part of the Earth every day. So they get around the world about every 90 minutes or so, but they're not, it's not like an exact circle, so it's going to kind of rotate around, and then, but we do hit like the points that we want to target the same time every day. Normally for high value stuff, we try to make sure it's like right at 10 a.m. So that way you get that nice early morning picture. Sorry, I'm kind of super into our imagery, and you'll know why soon when I tell you what I do. So yeah, this is what I do. I run our storage service. So I'm responsible for receiving the satellites from space, or the satellite imagery that comes down from ground stations, and then it comes to me. So I kind of have I'm a servant of two different sides. There's the spacecraft side, which is generating these beautiful images. And then there's the department that I live in that attempts to use machine learning and just math, like I don't know, machine learning, a lot of math, to actually detect when changes have happened in the world. We also are responsible for what's known as orthorectification. So when these satellites are flying around the world, they're, like I said, they're traveling at 30,000 miles per hour, so knowing exactly where you are down to the centimeter is very difficult. So what we do is we use machine learning so that way we have certain reference points on the Earth where we know exactly where they are. So we'll rectify one of the images in a satellite strip, and based on that rectification, we can rectify all the following images to know exactly where they are. But more and more, I'm moving less from serving the spacecraft side, where they can kind of put their images in and it just kind of scales, and which amazes them, and more on the kind of data sciencey side. And oh yeah, it's not supposed to say come join me, so ignore that part of the slide for a second. Yeah, right now we have tens of petabytes of data. We'll be at image mission 1 rates. We'll be collecting billions of scenes a year. So it turns out storing billions of high quality images is pretty easy. S3 actually makes that totally doable. What's harder is having a database which stores information on billions of things, especially in the cloud, also known as the world of very small computers. I want to talk a little bit about how we did this. I recently got a new person on my team, and I made her draw this image. She'll be watching this video, so Nika drew that image. And this is basically the architecture of how we do things. Before, when I came along, we kind of just had this storage system. They put stuff into storage, and they were like, "Oh, hey, this doesn't scale. Why not?" And I think no one had really kind of decomposed what it means to just be like the storage service. But mostly, what I do is two things. We have a catalog of all the images that we collect. So I'm going to walk away from the mic and point for a second. So that's really this stuff, the SC storage catalog. And that's just a bunch of webheads attached to Postgres. Nothing too fancy there. The row sizes are like 200 bytes. About 100 bytes of that is the Postgres geometry. I don't know if you guys have ever used Postgres before, but people used to use Oracle for GIS stuff, but it's becoming more and more the standard. Those rows used to be about 100 kilobytes. So all of you in your head can think 100 kilobytes times a billion is 100 terabytes. You don't put 100 terabytes in your RDBMS. So the first thing I did was split out that metadata. So we moved all the metadata or descriptions about those images into this extended metadata system. Right now, we can kind of scale that with super sharded MySQL. Probably going to have to figure out something that scales better than that as we get past the tens of terabytes of metadata. But once the scene is ingested, we put it out of Kinesis, and then that actually gets streamed into stream sets. In production, we're running their last release version, but I'm happy to report that I pushed a developed Docker to our staging infra, so it works. Thank you very much. And then stream sets is responsible for getting the data into Elasticsearch, and they gave us access to one of the S3 modules, which is now available. I think generally S3 destinations available generally. So we were actually creating a log of every change to our system into S3. Which is actually super convenient. I kind of trust Amazon and Kinesis and all of my infra, but just knowing that I have a record of every mutation that's happened into my system allows me to sleep better. Kirit and I were talking earlier, and I claimed that DevOps was the art of building an undo button. So since S3 is the only durable store on Amazon, as far as I can tell, having an undo button based on S3 seems pretty cool. That's the big idea. Most of our data science happens kind of at this S3 level, but bizarrely, I would say almost all but our data science people, most of the consumers go through Elasticsearch to access our data. I say bizarrely because I'm not used to these like fancy, it's easy to get to your data, you don't have to know how to write code universe, but the people who write Node.js at my shop really like it. So I have to say that it works pretty well. Once again, we have to be smart to keep our Elasticsearch up, but it works. And then finally, we have this kind of line that goes sideways that says downstream stats. So this is kind of hand-rolled state machine style programming. So users will kind of just listen to the stream of events and try to keep track of how many scenes in a strip have water in them, how many scenes in a strip have cars in them. I'm going to keep it abstract because I don't know how much I can really say about what we track the changes of. Let's see here. The current challenges, it's not so interesting. So the real thing I would say that is our next real step, here we go, is actually moving all of our hardcore data processing to GPUs. So if you are experienced, I should take a step back. Our orthorectification, we normally have about 5,000 to 10,000 nodes at a time, constantly churning to do real-time orthorectification. But they're like little cloud nodes. It's not like 5,000, 10,000 computers. We actually wrote a program that plays the Amazon spot market. So we actually take advantage of low spot prices when we can and all this type of stuff. But we've reached the limits of that. We basically eat up all of US West 2 spot market, so stay off of US West 2. So we're probably gonna have to move most of that to GPU. We think that we can do it with a couple. I have a friend from Baidu who claims all I need is a rack of GPUs and I can keep up with 10,000 machines, but we'll see if that's true. So if you want to talk about that, it's cool. And finally, the way that our system currently works is we put data in the database and then we put it into Kinesis. This scares me. I don't know if you can tell from this talk, but I'm paranoid about my data. And there's this small, tiny period where the data's in the database and not in Kinesis. So I am here to announce this tool that we're open sourcing. It's recently named JSONCDC. I I should say myself is open sourcing. It's written in Rust. I don't know if any of you guys are Rust programmers, but it's or if you've ever used Postgres logical decoding, the idea is the thing, that Kinesis stream, which you can think of like fancy Amazon, Kafka, or Flume, or something like that maybe, now partakes in the two-phase commit protocol of Postgres. So we know that if DB commit succeeds, the data has successfully been put on the Kinesis queue with this. It can be, this right now mostly just actually puts data, the one that we're using just puts data into a file in JSON, and we trust that file, and then we know that that file will eventually flow onto Kinesis. But I think the goal is to actually remove the Kinesis hook altogether and just put it right through a StreamSets API. So that way you could actually imagine having an ETL tool like StreamSets, which is partaking in the two-phase commit of Postgres, so it can be consistent and with, with certain in-order guarantees, you can guarantee in-order processing. So check that out. I guess someone will link to that. So the other thing is we do intend on open sourcing all of our code. There's still some legal issues with us open sourcing the code that runs on satellites, so write your congressman about that. But everything else we intend to open source it for the next year or so. We write a lot of code, but funnily we're an aerospace company and we want to give back, and I don't think that my little Python or my little Rust code is going to keep people from competing with us. So finally I wanted to leave you with kind of a notion of what's available today. So you can play with your own Planet Labs data. We've opened up access to all our data in California. So you can access all of this imagery for free. So as I said, the data comes in this unrectified way. We create scenes and mosaics out of those scenes after it's been rectified. The orthorectification I told you about is automatic, but the mosaic in here, creating these large mosaics like you see in Google Maps, that is still usually manual for most companies. We have some manual process, I should say rectifications. I think we're the only people who do automatic rectification. It's still considered impossible. But we do automatic rectification, and the mosaicing processes built off of it are mostly automatic now. There's some manual input. And all of that data, including I think our near IR, I don't know yet, is available through our API. So you can kind of explore data with you would Google Maps style with a Mosaics Explorer. There's also the Scenes Explorer tool, which I've never seen anyone else make, and it's kind of like the time machine for an area of the world. You can see how the world changes over time and see the different bands. And then we do have an open API. I think our goal is hopefully GIS companies or people who need geodata can use this to power their applications. Once again, a plug to come work with me at Planet Labs. I think we made the deal that Arvin gets the Java people and I get the Python people. All right, cool. Any questions?
What's the business case?
How do we make money?
More or less.
So the imaging business is a multi-billion-dollar business. There are a lot of public companies in that biz. We mostly compete in the agricultural space with near-IR scientific data, and also we do some work with some hedge fund folk. There's probably also some people who do mapping who might use our data or something. And in general, it's kind of the whole gambit. We're not going to give all of our data away for free, if that's the question.
Have you guys considered using Elastic as your master instead of Aurora?
Oh, yeah. So the actual like storage source? Yeah, so I think that is actually going to end up being S3. We're reaching the limits of like Sharp MySQL. That's an interesting question. In my world, Lucene, I've never used Lucene Index as my primary store. I always have like some other place that I put them, and then I have the ability to recreate and re-snapshot Elasticsearch really quickly. I'm pretty sure, yep, every part of that infrastructure has been destroyed before. So the ability to, the only part that still stands is S3, and we're only one hacker away from losing that. So for us, we really, like, our big notion of Elasticsearch is the snapshot and restore model, and we actually don't even resize live clusters or anything like that. We just boot up whole new clusters and load the data in, stream the data to both of them, and turn off the old ones. So we're probably a little bit paranoid about it, but the problem is if we had the capability to validate our databases were in a correct state, we probably might do it differently, but that's how we currently do that. The real, most of the time that the data gets stored out of Elasticsearch, these bottom stores really are just the place where we keep data so that we hopefully never read there. The scene catalog, that's not true, the Postgres on the bottom left does actually get some use. One of the guys who I work with, Frank Waterdam, he's the guy behind libtiff and libpng and GDAL, has a lot of integration into Postgres at the actual, at the driver level. However, what's hilarious about all this is that our front-end website, I think all the Geo Queries go against Elasticsearch. So, yeah, kind of funny. But for traditional like mosaic and rectification, they're more old-timey. They don't like those fancy distributed databases. They want that, and that's why it's really important for us not to have big rows in Postgres. Like I said, like 200 bytes now. I'd like to see it to a 100 byte row. Getting much bigger than that is going to be pretty much our doom, unless someone here who maybe works at Amazon can convince them to have bigger nodes. That'd be super sweet.
6 terabytes.
Yeah, my buddy at Intel said I'll be able to buy a box with a petabyte of memory, so maybe we'll just put it on one giant machine soon. Cool. I'm curious actually, there's probably some Apple, Uber, or any of those people here, if there are any secret Geo people in the audience. Anyway, you should bug me afterwards so that we can talk to see if any of this data might be useful for you. Cool. Any other questions about storing data? Sorry, petabytes. Oh, what's up?
Have you experimented much with the Google storage services? Like, would you be able to swap it in and out for one user?
Great question. Google Cloud?
Yeah, any of their storage services.
Yeah.
Could you repeat the question?
Yeah, I will repeat that question. It's a great one. So I referenced some Amazon stuff here, complained about Amazon 3 times. Why not Google Cloud? So we actually use Google Cloud as our DR endpoint, or as a DR endpoint. My boss really doesn't want to lose all this data. Did I mention I really care about this data? So all of our data is on Google Cloud, and I'm actually pushing our front-end guys to look at moving their infra over there. Not for the best technological reasons, although I think they like a lot of the technology over there and the scalability of certain stores. Would be super cool. I've heard my buddy said they're going to open source, or not open source, but release Spanner. I don't know if that's happened yet. Should be great. But mostly just because what they do is so different, I would love a clear boundary so that their APIs don't cross over to other departments' APIs. So I do expect that we'll probably have some GCE. We also have ground stations across the world, which means we have data centers around the world. We are trying to build out significant data center presence in Iceland as well, but we're waiting for the WAN links to Iceland to become big enough. The last time we tried to move our data there, we took out the country. So we are going to wait for that one. But I think the stuff that's going on with Iceland data centers is awesome. People who are only moving hundreds of terabytes should consider it.
So which are the typical geo queries that you see your user running?
Yeah, the question is what type of geo queries do our users run? So in my head, we have 3 types of users. We have people who pay us a lot of money for almost all of our data. Like if you're making some type of map thing, you might do that. Those people have kind of like we basically give them a whole clone of our infra. We don't want to know what images they're accessing, especially if they're like government or something like that. But like, and so it's tough to say with those guys. With direct APIs, it's generally the Google-ish mindset. So they're not like asking for like, tell me the centroid of this scene or anything like that. They're not, the user isn't doing those types of complicated queries. It's pretty simple in terms of, I wouldn't say like key valuing on like a 2D map. It's not that simple, but I mean it's thus far not that complicated. Lat, longe is the criteria. Maybe 2 or 3 different types of projections. We do support a bunch of different types of projections. Most of my users are internal customers. So the people generating the mosaicing or rectified images. Those geo queries are, I can't even hardly read them. It rises into, GIS is this whole field that people have been studying for a long time, and there's a lot of complicated stuff in there. But generally, you can kind of, I like to think you can generally think of them as, am I running out of time? You generally think of them as like pretty simple like linear algebra operations on top of map queries. And most of the queries that they do in my database is not really how do I like get things to automatically fold together, but kind of understanding like how does one scene affect the scene beside it, and how do they get mapped up into a clean mosaic. Does that help at all? Maybe that could be specific. Okay.
Are these 150 satellites constantly streaming data?
So they are not always connected. We're not up to that many in the sky right now, I think. So they only have 30 ground stations that they can talk to. And when they are in, it's not line of sight, I can't remember the term for this, but they have to be in range of a ground station to upload or download. That is our major limitation on the amount of imagery we can have. Also, please write your congressman. This is, the fact that this bandwidth is limited to space is crazy, right? Like, who am I gonna be interfering with? The aliens? And they've got better radios anyway, so what do we care, right? But so yeah, we're currently limited on the capability of, or the number of ground stations and the physics of RF. I think that we nonetheless will be able to improve our data rates, hopefully by an order of magnitude or so. I would like to see our data to be fully uncompressed, or not compressed at all, or at least only lossily compressed in space. We currently have to, I don't think I can talk about that, actually never mind. But yeah, they don't come down fully uncompressed, and that bothers me because I really care about these images and the whole notion that we might lose, we spend all this time to build a spacecraft and launch it into space, and then to not care about every single pixel. I don't know, it's really hard. What's up?
We have time for one last question.
Oh yeah.
How much does the spacecraft cost?
There's a specific thing I'm supposed to say with this. orders of magnitude cheaper than anyone else who has done imaging has done, is what I'm allowed to say. So an imaging satellite costs, like a good one, $250 million. We are not, we like what Crunchbase says is my company has raised like 200 million total, and a good deal of that goes to putting them into space. So I think you could probably guess the order of magnitude of what they cost from that. Thanks, Joel.
Thank you.